Hi, potential energy is just basically stored energy. It's energy that's there, but it's not doing anything. It's not being used. It's sort of like this. Have you ever seen that conversation happen before where somebody comes up and goes, a big sigh. You have a lot of potential. And then the next word is usually but. What they're saying is they see something in you, but it ain't happening. There's ability, but you're not using it. So it's in potential. Now for us in physics, there's all kinds of different potential energies. There's electrical potential energy like in a battery. There's chemical potential energy like in bonds, like in food. Mechanical potential energy, like maybe there's a compressed spring. And then there's gravitational potential energy. And that's what this video is going to concentrate on, is gravitational potential energy. Gravitational potential energy is from where you have an object lifted up so that it can fall. And as it falls, it can do work on something. So it's energy due to an object's position or situation, where it can fall down or roll down a hill or do something like that. And the way we find gravitational potential energy is mass times gravity times height. Now I usually use PE for potential energy because it matches. But in a lot of textbooks they use U, a capital U, for potential energy. So you may see it either way, but it's still the same equation, mass times gravity times height. And for me, I'm going to use 9.8 for gravity. Mass has got to be in kilograms and height has got to be in meters. So if you do that, the basic unit for potential energy is the joule, which you usually abbreviate as AJ. And 1 joule is equal to 1 kilogram meter squared over second squared. Let's look at some examples of potential energy. For this first one, we've got a 7 kilogram rock lifted to a height of 6 meters above the ground. What is its potential energy in the Earth rock system? This whole part in the Earth rock system, that gives you a framework that we're comparing it to the Earth. Because just an object by itself out in space wouldn't have any potential. It couldn't do anything. It'll just float there. It has to be in reference with something else. But in the old days, we would leave that part out when you just simply say, what is its potential energy? And you could still see that today. But let's look at this one. All right, we've got potential energy equals mass times gravity times height. Mass, 7 kilograms. Gravity is 9.8. And the height is 6 meters. So, couldn't be easier. Simple plug and chug. 7 times 9.8 times 6 gives us 411.6 joules of potential energy for that system. No problem, plug and chug. But look at this one. I've got a 7 Newton stone 20 meters above the ground. And again, I want its potential energy in this stone earth system. Well, here's the thing. If we look at the equation for potential energy is mass times gravity times height. In this problem, a 40 Newton stone, from that phrasing we know 40 newtons is the stone's weight. Not mass. Mass is in kilograms. That's its weight. But here's the neat thing. Look at this equation. Mass times gravity. Weight is mass times gravity. So we don't have to convert this to mass, because if we do, we're going to turn around and multiply it by gravity again. So this whole thing is weight, and that is 40 newtons. And so we just have to multiply by the height, 20. And so we get a potential energy for this system of 800 joules. So that makes it a lot easier because you don't have to break that back down. Let's take a look at a couple of questions where we already know the potential energy, but we need to find something else. So on this one, we've got a box that has a potential energy of 735 joules with respect to the Earth. So it's the box Earth system. And it's 15 meters above the Earth. What's the mass? Well, we got the same equation, potential energy equals mass times gravity times height. But in this case, we know the potential energy is 735. Mass we don't know. Gravity is 9.8. And we're looking for a height which is 15. And so we got to find the mass. Well, simple enough. 9.8 times 15 gives me 147 m. And now we simply divide 735 divided by 147, and we get a mass of 5 kilograms for that box. We've got another one here where this time we're going to find the height. But it's essentially the same process. We've got potential energy equals mass times gravity times height. Potential energy in this case for the system is 2,940 joules. Mass of the object is 12. Gravity, 9.8. And we've got to find the height. So 12 times 9.8 gives me 117.6. Oops. And we're going to divide. And we get a height of 25 meters. So again, simple plug and chug. Get the numbers in the right place, you'll be fine. But what if we don't have much in the way of numbers? What happens to the potential energy of an object if you triple its height above the Earth? Potential energy is still mass times gravity times height. So everything stayed the same except for the height. It's 3 times further up. If this is 3 times as much, these are all the same. So that means our potential energy has to be 3 times greater. So if we triple the height, we triple the potential energy. If we have another one over here, let's look at this one. We've got a certain object, a certain height above the Earth. At this height, it has a potential energy of 30 joules. Okay, so we got our one object. It's got 30 joules of potential energy. We've got a second object at the same height, so they're both the same height above the Earth. So in their system, they're the same height. This one has a potential energy of 30, but on this one, it has 4 times as much mass as this one does. So what happens to its potential energy? Well, potential energy is mass times gravity times height. So everything stays the same. Acceleration due to gravity is the same. The height is the same for both of them. But where one had a mass and it gave an energy of 30 joules, the other one has 4 times that mass. So we'll end up having 4 times that same energy. And so the potential energy of that second object will be 120 joules. These are pretty linear. If you double this, it'll double that. If you triple this, it'll triple that. If this has half as much mass, it will have half as much potential energy, as long as everything else stays the same. Thank you, and tune in again, and we'll do some kinetic energy equations. Thank you, and goodbye.